Okay, so this problem was a bit tricky, like a lot of other problems. Yeah. Okay, so let's start. What I did was start by drawing the contraption we have. Okay. I'm going to call this alpha. I'm going to call this length right here, I'm going to call this entire length A. And then I'm going to call this horizontal length right here D. Okay. They give us mass is equal to 12.5 kgs. B is 4.7. Beta is 37 degrees. Time it takes for it to revolve all the way around is 4.8 seconds. So R, I'm just going to do a little bit of geometry right here off the bat. R is going to be B sine alpha, which is 3.754 meters. A is going to be B cosine alpha, which is 2.828. And then finally D is going to be A sine beta, which is going to be 1.702 meters. Okay, so we want angular momentum in the z-axis. So we're going to say H, z is equal to I, z angular velocity around the center of mass. Okay, what we can do is do some simple stuff first. Let's calculate the moment of inertia. I is equal to okay. It says assume the rods and spokes are massless and you can treat the wheel as a ring of radius r. If we have a wheel that's treated as a ring of radius r, the moment of inertia for anything with that shape is going to be mr squared. Wow, this is nuts. Mr squared. Which, if you plug in the values, gets you 176.12 kilogram meter squared. Okay. So now we need to find angular velocity. I'm going to split angular velocity into two components. There's one rotational and one revolutional. So I'm going to call it WR and WE. Wow, this one sucks as well. Okay, so let's do WR, which is rotational. We have the total distance traveled around in a circle, if you can imagine it, is going to be 2 pi b. Total angular distance is going to be 2 pi b over r. And then total time traveled is 2 pi b over r t. So that gives you the rotational, and this simplifies to be 1.64 radians per second. Okay, and then we want revolutional. We want the wheel rotating about the fixed point O, but we want it on its center of mass. So we have W E is equal to, again, 2 pi d is the total distance traveled, but we're using d instead of b now because we want it about the center mass. And yeah, and then the total time stays the same. It's over t. Bruh. I'm just killing off markers at this point. There we go. This gives you 2.228 radians per second. Now if you subtract them, you get W is equal to WR minus WE is equal to and now if you finally take this value, multiply it by IZ, which is the moment of inertia, you get your angular momentum in the Z component. So HZ is equal to negative 103.55 kilogram meters squared per second. I hope this is the correct explanation. I don't think so, because I checked and I don't know why my answer differs by 1. I don't think this is the correct explanation, however, but
what happened is we have to look at because the wheel is rotating about itself, so
yes.
you have to take into account the circumference that is being traversed there.
Oh, I see.
Isn't that like generally the two different methods? One is
I think
it's not just one rotation that is happening
Oh, it's like
on the
5,
wheel
6 times.
in the entire time.
Mhm.
This is correct.
This part.
Yeah, because
Okay.
it's going through one cycle and coming back to the same spot.
Yes.
So its period is t.
Okay.
But the period for the other one is not t.
Oh, it's t divided by.
Yeah, is that ratio of the
Right.
two radii.
Okay. So would be. So if it's full t is
Because
this.
it says that
Yeah.
the wheel rolls.
Yeah.
So that's the key to say that
Yeah. Okay.
it's probably having more number of rotations.
Yes. Okay. So it would be something like b over r t.
You would still have the 2 pi.
Okay. You want the time?
The key is that the same distance is covered
Yes.
by the points, so
Yeah.
you can use that to equate the distance covered. So that you already have the distance covered there as 2 pi b.
Yes.
So what is the distance covered on the circumference of the wheel?
2 pi r.
that's for each revolution, right?
Yeah.
How many revolutions does it take? So you can find out the number of revolutions that it takes.
2 pi b divided by 2 pi r.
Yeah. So your V by R ratio that we have there already gives you the number of revolutions it has taken.
Okay.
Yeah. So that times 2 pi by t gives you the angular velocity. So that's correct.
Okay. Yes. Oh, okay, okay, I see. So use this instead
See,
of
if
that.
it was just one revolution, it would be 2 pi by t.
Mm-hmm.
Now that the number of revolutions is more, you have a V by R factor.
Yeah. Okay. So you use this instead of that.
Oh, wait a minute. You already have that there. Okay. So I see what you're saying. So you already have that there. So the other one should be just 2 pi by t, no d there.
Okay.
Right? Yeah. So you already have that.
2 pi by t. Okay, that's gonna be the total amount. Okay, I see.
So probably will have that calculation right there. Right? 2.228 is not the one.
Yeah. Yeah. What is 1.30?
Yeah, it's one less. That's how you get.
No, no, it doesn't. You multiply 1.30 what? 309.
Right.
Yeah.
Oh, no.
Okay. Once you have these two, how do you subtract them, right? To
No, they are at different angles, right? So that's why you should recognize they are vectors.
right. Okay.
If you write them as vectors with the appropriate unit vectors, then you will see you can actually find the actual.
Okay. So this one goes in which direction? The
So introduce coordinates,
Yeah.
unit vectors.
okay.
You have
So z. I'm just gonna do k hat.
from that.
X.
Now you can
Okay.
introduce an earth fixed set of unit vectors as well. That's at O. At O you
Yeah.
can mark earth fixed set of unit vectors.
Okay. So this is j hat. That is k hat.
No, don't straight up.
Oh, I can have it straight up.
Well, that's the direction you're first in the velocity.
So vertical and the horizontal.
Okay.
You can call it E1 and E2 maybe.
Okay. So this one goes in the, let's see, E1 hat, yeah.
No, that goes to the K hat. That's the number of rotations the wheel is taking around
Oh,
itself.
that's the
right?
real one.
Say
Yeah.
V by R number of revolutions it's taking.
Mm-hmm.
It's about the axis of the wheel. So it's along the
Okay.
axis.
But this is in the axis of the Earth, so it's going to be in the
E1 hat.
E1 hat, yeah.
So you can mark both the angular velocities as vectors and put the K hat and E1 hat.
Okay. So
Underline the
yeah. K1. I'll just put K1 hat here, and then vectors E1 hat. Okay, now we have to basically get E1 hat into components of K1 hat. Or K hat, sorry.
You are asked only the Z component of the angular momentum.
Which is this, yeah.
So, but it will also have a contribution from the E1 hat, but it will not be the entire thing.
Right.
It will be a part of it. So you need to find that component.
So it would be,
You can subtract that. Yeah, you can remove that.
okay. So we want it in this tab. We have it here. So this would be k hat cosine, or it would be this cosine of beta. So, and then subtract because, or would it be subtract? It would still be positive, okay. No, it should be a subtraction though. At some point it should be a subtraction.
What's beta?
Beta is 37 degrees.
Okay. So I got 1.45.
For,
If you do
okay, 1.04. Okay. What is it?
It's 0.595. And then when you multiply it, you get 1/4.47, but I'm using rounded numbers, so. But it should be negative.
It should be negative. Yeah, oh, right. That's true. Is it because everything is pointing towards the origin? So it's away from the k hat direction?
Based off your definition.
It's based on rolling, so
Yeah,
if it rolls in a particular direction,
Yeah.
which direction would the larger circle be?
sorry,
Assume the wheel is rotating in the k hat direction. Right?
yeah.
So then, what direction would it go on the ground?
It would go, if you're looking at it from above, it will go clockwise. Okay.
Which is along the negative.
Oh, I see. So this is, but yeah, this would all be subtracted. Okay.
And then, so it's negative 0.95.
Yeah,
When you multiply it.
yeah. Okay. And then you multiply by I. Yeah. Okay. And then multiply by IZC, and you get what? Negative 104. All right. Thank you guys for helping me with this.
Okay, so for this problem, we have to find the s component of the angular momentum vector about the mass center. So to do that, we use this equation. Which is just the summation of the negative summation of the mass of each individual bar times their center of mass on the x coordinate and like the z plane.
Are those the distances? X, CI, and BCI?
Yeah.
On the X component.
Where am I? Okay. So first, I just like found the center of mass of each bar. 4, 5, 6, 7, 8. Now, after I do that, basically I have to take the product of the x coordinate and the z coordinate, and then multiply it by like the mass of each bar, but the mass of each bar are all equal to each other, which is like 0.7 kilograms. Yeah, so like all I have to do is just take the products of these and like add them together, then multiply it by the mass, then take the negative of that. So come on, marker. Thank you. Okay. For the sake of space, I'm going to leave out the terms that that have like a zero in either like the x coordinate or the z coordinate because they turn out to be 0 anyways. And this is equal to 5.054. But then to get the angular momentum, we have to take, please write. See, you have to use this equation. So we have to use the inertia and multiply it by the angular speed that was given. Which gives you the answer of 30.324.
So one assumption that was there was that C is P because of the symmetry that you have. Yeah, so that should be stated up front that the point P is the center of mass. Otherwise, you need to calculate the center of mass.
Oh, okay.
Okay.
Yeah.
All right. So this question was relatively simple. We just had to implement a formula.
Just before you start,
Oh,
I
okay.
think, yeah, you have
Yeah.
So here the IXZ, which is summation of MIXC is the moment of inertia of each slender rod with respect to its own center of mass. So since you're calculating moment of inertia with respect to P, you'll have to use the parallel axis theorem to do the plus md square.
XC by it's the distance.
Yeah.
ZC.
Yeah. So because of the symmetry, it will get cancelled out. Is it like m?
No. This is what is the parallel axis theorem.
Okay.
Because the XC, the actual IXC is 0 for all of them. Each of them about their own center of mass, it is 0 because of symmetry. So whenever you have a symmetric structure, you will have all products of inertia going to 0. So whatever is there is
This
purely
the only
due to the parallel axis
theorem.
theorem.
And for MX CZC, right? Those are distances from P, right?
That's
For
correct.
each rectangle.
Yeah, correct. Because you want it above the x-axis.
X component of
Oh,
And it's rotating about. If you wanted about z, then you would do adjustment.
Okay, this question was really simple. We just had to implement a formula, so I will just write down what we were given and then what we had to do. So we have an aircraft with angular velocity given by roll P. Oh, this is pretty bad. Or are all of them bad? I don't know. Let me try this one. Okay. Yeah. So P is 0.15 radians per second, and this is the roll. And then Q, so the pitch is 0.18 radians per second, pitch. And then R is 0.19 radians per second, and that's the yaw. And they gave us the moment of inertia matrix. And it's all in 10 to the 6th kilogram meters squared. And so we know that the moment of inertia, and firstly they're asking for the angular momentum in the roll direction. And we know that when they gave us the moment of inertia matrix, the form of it is you have the moment of inertia of xx, then you have xy, xz, then yx, yz, and then zx, zy, zz. So when we're talking about the roll, we're talking about the x direction, and you get that from the roll itself from P, except you will also get roll from the pitch and the yaw, because if the moment of inertia of x, y, and xz are non-zero, then they will also contribute to the total angular momentum. So the formula for that, you take each component that has x in front. So the angular momentum of roll, the formula is you take ixx times the roll. This is purely from the roll. And then we have the other two terms that are from the pitch and the yaw that also contribute if the moment of inertia are non-zero. So we have xx and xyz as the top row here, and we have pqr. So we just plug in really, and we have 1.1 times 10 to the 6th. Oh, of course you could also, I guess since you want it in terms of 10 to the 6th, you can leave it out. So yeah, I'll just write 1.1 as it is. 1.1. I just divided it by 10 to the 6th at the end. So I'll have 1.1 10 to the 6th kilogram meters squared times 0.15 radians per second. And then plus, this one's 0, so this actually doesn't contribute. So you have 0.0 10 to the 6th kilograms meters squared, and then that's times 0.18 radians per second. And then we have xz, which is just 0.2. So 0.2 10 to the 6th kilogram meters squared times 0.19 radians per second. And if we sum this, we get the angular momentum in the roll direction to be 0.2030 and 10 to the 6th kilogram meters squared per second. Yeah.
You typically will have this kind of form for most aircraft, conventional designs. So, because there's a plane of symmetry, a vertical plane of symmetry, which will make those two zeros. And also, if you look at the ordering of the diagonal terms, it will typically be in that that you will have the first term xx smallest and then the next biggest and the largest. Because about the x-axis, almost all the mass is close to it, so it will have less moment of inertia. For the z to be the fastest.
This one's a duplicate of the other one.
Yeah.
Entirely?
Even the answers.
Same with the next one.
No, this is also a duplicate.
That one's also a duplicate.
This is my fault. All right, I'm just gonna quickly draw this over here. So. So we have some important points. This is the origin, point O. This is point Q, which we're going to find the moment of inertia of this object with respect to. This is the center of mass of bar A, so bar A has a length of A, and it's got a mass of A, which are also given. B is the same things. And then I'm going to call this one D, so MD and LD. And we're given all of these values, so and the general formula that we're going to use for this problem is that the moment of inertia about Z of Q, or about Q, is the sum of the moment of inertia about C, about the object center of mass. So C is denoting each individual object center of mass, plus the mass of the object times d squared, which can also be written as x times the distance from Q to the center of mass, which I'm going to call Qi in this expansion, plus y, Qi. So this is just the parallel axis theorem in a more general formula, and we're going to apply this to every single rod. So first for rod A, the moment of inertia of a rod spinning about its center of mass, about the z-axis, is 1/12 ml squared. So let's see, the total moment of inertia about Q. So for the first rod, 1/12 m/a squared. And then for the parallel axis theorem, it'll be ma, and then the distance from Q to the center of mass of A is LA over 2. So we have LA over 2 squared for the x distance, and then the y distance in this coordinate system is 0. So plus 0 squared. Okay, now for the second bar, again it's 1/12 mb lb squared plus mb, and then the distance from Q to the center mass of B in the x direction will be the full length of this rod. We're going from here to here, so we go first the full length of LA, so it's LA squared, plus, and then in the y direction, we go half of the distance of B, so it's going to be LB over 2 squared. And then for the last rod, since it's rotating around the z-axis, a slender rod does not have this component to it. It only has the parallel axis theorem. And that's for a slender rod spinning about its central axis. So we just have this component. It'll be md times, and then the distance from here to the center mass in the x direction is L again, LA, sorry. And then in the y direction, it's none, so 0. And then you plug in everything. So LA is 1 by 2, like you just plug everything in. I don't want to do that because it's just a ton of work for no reason. And that comes out to 11.2067 kilogram meter squared. And then I also have the next problem, which is kind of similar. We just have some different values though. And we're going to use the product of inertia formula, very similar to the one that Chanel had. So the product of inertia at xy, about a point Q, will be negative of the summation, or I guess, sorry, it's better to do the summation of negative m of every individual rod times its x position of its center of mass, the distance from the center of mass to Q, times its y position, again, the center mass to Q. Okay, so we have to do this for all the bars again. So the mass of A is ma. The distance in the x direction is negative L over 2. Here we actually have to factor in the negatives because before we were squaring the distances, so negative, positive didn't really matter. We could just do the magnitude. But here you're just multiplying by the scalars. So you do need to factor in the negative. So this would be negative LA over 2. But it turns out this doesn't actually matter because its distance in the y direction is 0. So this whole thing actually goes to 0 for the first rod. For the second rod, we have minus the mass of B times, again, it's negative the full length of the initial rod, the first rod, so negative LA, times, and then how far do we have to go in the y direction? Well, that's LB over 2, positive because of this coordinate system. Okay, and this doesn't go to 0. And then the last one is the mass of D times, we go the full distance again, we're trying to get here, so it's going to be negative LA, but then in the y direction it's 0 again, so this goes to 0. So we just end up with MBLA times LB over 2. And this comes out to be, plugging in, 2 kilograms, 1 meter, 2.2 meters, 2.2 kilograms times meter squared.
Okay. So for this question, we're shown a thin plate with density rho and thickness t. Calculate the product of inertia about O, assuming the rho t equals 1 slug per inch squared, and then we're given the length of A and B, and X and Y are the axes on the plate. X towards the right, Y towards the top, or towards up. Yeah. Note. So basically, this is just basically how you would approach the problem. So we split the plate into 2 rectangular plates, whose center of mass and moments of inertia are known, and they say the mass of each plate is equal to the area. And note that the products of inertia of each about their center of mass is 0. So the moment of inertia for the center is 0, but you have to use parallel axis theorem for each plate. So I'll draw out the. What's this? Okay, so I have this. These are 1 inch. And you can either, I guess, split it here or here, but I just chose to just split it off here. So you have 2 rectangles like this. okay? And we'll call this like plate 1 and then 2, okay? And this is length A, and this is length B. And I've also included another length, just LB prime, right here, which is just the length of the plate without the end. And we know that that is just LB minus the 1 over here. So LB prime equals LB minus 1. So to start here, I'll write out, or actually, yeah, sure, I'll just write out what they gave us. LA equals 6.1 is LB equals, and then so for the moment of inertia, you would do the mass of the plate times the distance, I guess, from the center of mass of X and Y. And they told us right here the mass of the plate is equal to the area. And so just for like my notation, I just wrote it as A and then dx dy, because I mean, because it's pretty much the same thing. You have the area as the mass, and then I just noted the X and Y as the, oh right, sorry, yeah, forgot that, yeah, negative, yeah, so this is what I have. And so we just do that for each plate, and then we sum them. So for I, X, Y, for the first plate, you have to have it by the center of mass. They gave it to us as 0, so for the next step, I'll put it as 0. And then we have plus negative A1, dx1, dy1, and we know that this is 0, and then negative A1, we have negative LA times 1, so LA times 1, times dx1, which is just 1/2 from the center because this is 1. And then dy1 would just be LA over 2. And from if you just plug in LA as 6.1 inches, you'll get negative 9.3025 slug inches squared. Now for IXY2, it's, oh, I forgot to put 1 here. Yeah, but it's the second one with respect to the center of mass plus negative A2 dx2 dy2, and we know this is 0 as well. And you have, for the area for this one, you have LB times 1. So I have, right, LB times 1. Now for dx dy, you have to take into account this 1 over here. So, well, actually for x you have to. Yeah, so for x, we have so LB prime over 2 for this part, but then you have the 1 as well. So 1 plus LB prime over 2. And then dy2 is still 1/2. Yeah. Because this is 1. Yeah. And if you plug that in, the LB being 3.0 inches, you get negative 2 slug inches squared. And then we sum these. Yeah, we sum these. So total for IXY is equal IXY1 plus IXY2. And you get negative 11.30 slug inches squared. Yeah. We can like go back to hers if we want. Yeah. So what's the next one then?
So, wow. Okay. I'm going to call this the y axis, and then going out the page is the z axis. And then in the other reference frame, we have the circle, it's tilted at an angle beta. And I'm going to call this the YC axis. This is the Z axis. And just for reference, this would be the Y axis. And this would be the Z axis. So we need to find the product of inertia I, Y, Z. And you can get that from M, Y, Z. And basically you can pull out the M, and the Y is going to be basically the moment of inertia of this around its y-axis, which is going to be 1/4 r. And then around the z-axis is going to be 1/2 r. So this is going to equal 1/8 mr squared. And to get it tilted, we use this formula. So I y c z c is equal to I y z sine 2 beta. Which is going to be 1/8 mr squared sine 2 beta. They gave us m is equal to 1.7 kg, r is going to be 1.2 meters, and beta is going to be 50 degrees. Once you plug all those numbers in, you get 1/8.
And this is as far as I got because I didn't know what to do. Because this question is asking us to calculate the smallest principal moments of inertia. And the closest I got to that was like an entire, like, full digit off. And I know it's wrong because it doesn't match the answer. So,
Anyway, do it and we'll see if we can correct it.
okay. Okay.
So this is a typo at the bottom. This should be equal to one. Yeah.
Okay. I'm going to start by like locating like the center of mass of, well, let me do this first. I separated them into like two different pieces. I'm gonna call this piece A and this piece B. Yeah. And then from like the little note at the bottom, it tells us that the mass of each individual plate is equal to its area.
Actually, it should be one. That's a typo.
Oh.
Yeah, on the top it's given rho p equal to 1. Sorry about that. On the top you see assuming rho p equal to 1 slightly per inch square. So that's what rho p is.
Okay.
Yeah. So this is right. The bottom.
Okay, I thought that as well, but are they still equal to like their areas, or are they equal to like 1, like the mass?
The mass is the area. The area said that.
Yeah.
Okay.
So because mass is equal to density into volume, so that includes the thickness.
Okay.
That part is 1. So it's just the area.
Okay. So the mass of A, to get this length right here, since I split these into two pieces, I know that this length is 1 inch, and then like this full length is 5.2. So this length is 5.2. So since the mass is equal to the area, the mass of rectangle A is 5.2. And the mass of B is 2.8. So the center of mass of point A with respect to O is 0.5, 3.1, and B would be 1.4 and 0.5.
No, not necessarily.
I have to get.
Everything has to be zero except
You'll
the
have a
diagonal.
few zeros.
Yeah. But in order to
Diagram should all be open.
in order to use the thing where the eigenvalues are diagonal, everything else has to be zero. So you just can't get the matrix to be done. You have to do determinant A minus zero.
Yeah.
Yeah.
Because you have all diagram terms.
Yeah.
Because this is not symmetric about the XY axis.
But it says the
So,
components
yeah.
inertia, these are the two vertical plates because of the reactors. So why would you not want that?
Because there's other.
Here's the dynamics system.
Yeah. Yeah, exactly. So each one is parallelized.
Yeah.
Okay. But they've given us the center mass when it's zero. So we just have to add on that other than AX bar. Right? Okay. So for one, let's just start with one. We have based off that drawing. And we have no wait. No, the plate is small. LA. Yeah. And then you do A minus lambda I like that. But we use parallel axis for each. So you use parallel axis for XX.
Okay.
The formula, the AXY basically.
First identify the ones which are zero so that you don't need to worry about
Okay. Cool.
which of the off-diagonal terms are zero.
Okay. The product of inertia about the other central mass was zero. Yeah. And then these two and these two?
No, she already did X. Oh, you mean Z? Yeah. And YZ is YZ. But everything else you actually calculate.
Okay,
There
yeah.
was one more plane of symmetry. IXY would have gone to zero as well. Then you could easily determine the lowest from the diagonal.
From the diagonal. I mean, it's not really like a math. Like once you get the matrix, I think one of us can build like a determinant
Yeah.
and then get that.
So
As long as we get it.
ratio of a rectangular prism, how the center mass is 112 times m times the distance from the whole.
I saw that equation, but I wasn't sure if we used it for like these.
I think that works. Or you could just do parallel axis here.
We do both.
Oh yeah. You do both. So just do one to I guess.
Okay. Hold on, what's the equation?
This one. For both, for x, y, and z, it's this.
Okay. 112 m. Come on, Margaret, don't fail me now. know what? Let me just like solve it out.
The points on the length of the whole object, not the distance this angles. That's for the parallel axis theory.
Ah.
And would you have to use it twice? You have to do it for each
Two ones.
yeah, so oh my god, that's so much.
Anybody want to put this in the calculator? Point nine what? Okay. Is it the same equation for? Cause like I use this for I'm gonna just call it IXX. IXX is this the same for IYY?
It has the same form, but it has different dimensions. Like
for this, and this is the z-axis, then you multiply it by the a and b distances. If this is a different axis, you multiply it by this and that. For the c-axis, you multiply it by this and this.
Oh, so you use B and C instead of A.
So I think you calculated ZZ on the first one.
That was
That's
easy.
ZZ.
Ah. Okay.
now I'm not sure how you do the other two. You could calculate thickness, but I don't know.
Actually, parts of it are already easy.
Just do like moment of inertia for a rectangle.
For a rectangle?
Isn't it? No, you treat the A as you treat the area as an axis. And then you just do each distance for the second.
Yeah, just do that as a rectangle.
So A distance in the X and distance in the Y. Is that the same? Yeah, see, this is like a 3D that's not. So you have to use the area one. So, but then how is and then okay, and then is like for X Y you use the X distance and the Z distance? Or,
Yeah.
For XZ, or sorry, for X and
For YY and ZZ, you would just use like the X and
Yeah,
just
that's
X and
zero
Y.
anyways. You only need IX.
okay, yeah. So use the distances for X and Z then.
Yeah. So it's the same. It's the same thing, but instead of the x and y distances, you do x and z and y.
IX. this case, whenever you have a thin plate, z goes to 0. So it just
Okay.
becomes y squared dm.
Okay.
Similarly, your Iyy is
X squared
integral of
dm.
Just x squared dm, and your Izz you don't need to calculate because it's the sum of these two.
Oh.
Plus Iyy only for thin. This is only for thin wall, thin structures. Okay. Because the other direction you have x squared plus y squared. Because the z squareds have gone to 0 here, therefore you can just add them up. You don't need to separately calculate your Izz.
Okay. Funny enough, I calculated all of these numbers last night, and I just didn't know what to do with them.
But you still have to do it
Yes.
Yeah, for these two. Would I use the center of the x coordinate or just like the length? Okay, that's what I assumed.
Yeah.
Calculator.
It's the integral of x squared dm, and
But our mass is not changing.
but for a rectangular plate.
If you take the integral of dm, it just becomes the mass. And yeah, it's sort of an x squared, right? So, and the mass is the area. So
So
area
dm is
times
rho t times dA. So rho t comes out as 1. So it's just dm, the dA. dx dy.
So if it's a dm,
So your dm is nothing but dx dy.
yes. Okay, so that's why I added same as
That gives you about the center of mass. You already probably have it. Then you have to use your mathematics.
Do I keep going or? This? I use, so like this is the length of x for plate A, and then I multiplied it times the mass of A, and then this is the length of plate B. Yeah, and in like the x direction, and I multiplied it times its mass.
No, wouldn't that be still be
No, the pointer is still there. The formula is not really ml squared.
The what?
Right, 12 ml squared, right?
Oh, it is? Oh.
And the formula that you get is still with respect to center of mass of each small atom. Yeah, you have to still use parallel axis theory. Oh yeah, but the one formula now square is not. It's
also are we using the rectangle one for or I guess oh no or just
do I multiply it by 1/12 or not?
Well, I think there's definitely a 1/12. Yeah, right? There's definitely 1/12. So put 1/12.
Okay.
And then well, it's done. Let's take it on there. And these go.
The distance would be
Right.
Because this is center of mass, this is the moment of inertia with respect to center of mass of each of the A and B, right?
Mhm.
But you're calculating with respect to them.
Okay. How do I do parallel axis theorem? Because I haven't like physically done a question on it.
So it's plus n into t square, distance between the moment of inertia of each of the bodies with respect to them.
Can you repeat the equation?
So it's mass of A, let's say you're taking it for A.
Mhm.
So it's NA into distance between the moment of inertia of A to O.
Okay. So
And then you can write as a
Sorry, center of mass of A to O.
okay.
So I go IXX total as 81.4.
From that or
I don't know, from these two.
After using parallel axis as well.
Okay. So you got what?
So remove the equal sign and just add a term. Yeah. Plus area times distance 1.
Okay. The distance of.
So then use the Pythagoras theorem. Area you know 5.2 into 1 times the distance the center, which is 3.7.
the A part is 5.2 times 1.
Area is 5.2. The distance is. Oh,
The distance is 3.1 from the center of mass of A to O is 3.1 because LA is 6.2.
The distance. The axis plus do that.
I think so.
Wait, which distance is 3.1?
Wait, I might be wrong. 2.5, 2.6, 3.6.
It's 3.6 and then the
Yeah.
No, you subtract. No. Don't you subtract the. No. Oh, yeah, right. Subtract the.
It's 3.6 plus 0.5. 3.6 squared plus 0.5 squared. Here, let me calculate that. I got 157.87.
You got 150 what?
157.87.
Also, would this be times or plus? Plus. Okay.
Oh, it's plus.
Then you have to multiply that by mass. There,
Which is the area.
area, area. So it would be like 3 point. Is that 6 or 1?
For what?
Center of mass.
This is 1.
Oh, yeah. Okay.
So like the mass of this is 5.2.
You also have to do parallel axis theorem for the block B, right?
Yeah.
So it would be
Am I crazy?
Where'd you get 3.6 from?
The distance of the center of mass of this from O. It's 3.6 when I thought about it because
Also, I redid the calculations for ICC and I got 14.2.
I really know. 1/12 is only the first number.
it's actually 3.6 just because like the center of mass of this is like 2.6,
Oh, you're
but
right.
like you have to add like the 1 into, yeah.
Right, I did the first one.
Oh wait. Okay, yeah. And then
IXX is
1.4 squared plus 0.5 squared times 2.8. Yeah.
Yeah, 83.302. I should be something similar. Let me just replace those like swap a couple dimes.
I would basically just put these same values up here, right?
Sorry?
I would just put these same values up here, right?
Yeah.
Okay. Marker don't fit in it.
Okay, so it's 73.615.
Not getting your grabs that. I think the parentheses are showing me that much. The 36.9 I got. I'm trying to put it in. You guys can continue.
Okay.
How do you calculate IXX, IXY, and IYX?
I think that you just do it yeah, I think you just multiply the coordinates of the center of masses by each other times the mass. Yes?
And the masses here, dx dy, so it's the area.
Yeah. So, and if I'm not mistaken, IX and XY and YX are equal to each other, right? XY, like IXY and IYX are equal to each other, correct? Okay.
I did not get that. So that's 5.2 times 1 squared plus 2.8 times 2.8 squared plus
guess.
Same as doing 112
So it's 5.2 times 2.6 squared plus 25 squared plus 2.8 times 1.4 squared plus 25 squared. That's one term. And the other term is 5.2 times 1 squared plus 2.8 times 2.8 squared. That divided by 12 is that one. All right, now I'm getting 77.4. And then the other one. I guess it's 77.14, right? Yeah, okay. So use that. Instead of 73.615, it's 77.143. 11.3.
Hold on. 77.143. 77.143.
Yeah.
And then what was this?
Should be negative 11.
-11.32.
Wait, I'll get it.
I got
See,
86.2.
just use that.
Let me see what's in there.
Yeah, 86.831 for the last, yeah. Let's see what's up.
Okay.
The smallest eigenvalue, yeah.
IYY.
The last one should be.
So did you check the 30, the first one?
I checked that. That's fine.
Oh.
That's fine. Yeah. You can check it. Check the point four.
Whoa. That's
Yeah, negative 11.32 is also right. And that would be the same too. So now you have negative, let's make sure that all the ones are right there. 2, 0, 0, 36.9, 3, 86. Yes. Yes. Now, did someone do eigenvalues on that? What did you get? No, what's the smallest one?
not small enough.
What is it? What is it though?
36.9. It's that one.
36.9.
Where do you think we made a mistake?
Yeah, I mean.
ICZ is IXX plus IYY. And also your IXX and IYY will not include both the distances.
Okay, wait.
So is XX only supposed to include the X distance to the center of mass, and Y is only to the Y
Wait, so let's
distance?
erase that part. I guess.
So just
So it should be 80.04 for IXX. Okay, here, you calculate, right? So you just put it, yeah, or take that out, yeah. That might be in the day.
alright, 3.6 squared, 1.5 plus
Okay, I'll do that.
0.5 squared times 28.
So don't calculate the whole thing.
Don't.
Calculate each one.
steps.
Do it in
Count
steps.
it in
Yeah.
Yeah.
steps.
I got 7.3.
Wait. Or which one?
Why?
One second.
Change that.
I got 70.35. Is that what you got to?
7.35. So I got.
Yeah, 70.35. We don't even need to do ZZ because it's just adding to others.
Yeah.
Yeah.
But the second one's also wrong.
second, second one how many that? I got 80.0423. But we have triple check here. Hopefully if that messes up then
I don't think I got that. I got something way smaller.
I'll tell you
But when you see that, I got 18.
there, okay.
Did you factor in the 112?
I did, but I got 18.73.
Yeah, 18.74.
Yeah, why is it that low?
Because we
Well, that makes sense because actually
By the way, the 1.1 is only for the first
Yeah.
portion, right? You're not doing 1.1 from parallel.
yeah, just for
No,
the first part.
But everything in the first parenthesis.
Yeah.
So 5.2, 2.8.
Yeah, exactly.
With
And
the
then just sum
parentheses.
those
For CC.
for ZZ. We have we have 89.09.
Alright, so I'm going to need you to read the 89.09 is CC. What's
YY is a 70.35.
70.25.
XX is 18.73.
Yes.
And then the other two are the same.
Yeah, 0 and then
89 is 1
okay.
That's
It's not? Wait, do that.
You can just make the third dimension out. And that's kind of like a trick.
Why?
Because ICC is IXS plus IY, right? So it's definitely larger than both. When you take eigenvalue, you'll be multiplying the third component. So it's just like
Wait, no, should 89.09 be in the top left?
No, that's CC.
Oh, wait, that's easy. Yeah, you're right. 18. Oh, okay.
Because one of the equations in AB is not
Yeah,
that
you
that will be factored in.
Maybe I thought it was values right out a lot. No, let's
That's
see.
already
That would be I just see it.
it's larger than XS.
That's not good.
Okay, which one is it? 1507.
150.
No, you divide by 10. Oh, yeah.
150.
Yeah, that's right. That's fine. Alright, wait. So go back to the previous, let's make sure everything, let's go through each one and see if we made a mistake. So, ZZ would be wrong if X or Y is wrong, otherwise it's not wrong. So, let's look at that. X and Y, 112 for the first part. And then the second part is just 5. You add that up. So at the top left you have 18.73. And then in the middle you have 70.35. And the last one you have 89.09. Those are all wrong.
Yeah.
you can do some calculations.
Yeah, yeah, yeah.
You do these two.
Top and bottom.
Yeah.
I still get 80. You get 13.017.
Then 2.8 LB in the y direction is 1. This should be a 1 squared. 2.8 center mass of B in the y direction is 25. That's y. Alright. So mass of B is 2.8. The distance, the length of B in the x direction is
Okay, got my
what's the length of B? 2.8. 2.8. Okay. Plus mass of 2.8 the center mass.
You prefer to write down values. Without new values.
This is going to be mass of 2.8 and the x direction is
Yeah, neither of us could have solved this by ourselves.
Yeah. 79.109. The top, very bottom. Then 0.933. Then I just did 1.7. And then the last one. Times 12. 2.8. Times 2.8 squared. That's the first one. And then 2.8 times 1.4.
How do we calculate
7.3.
IXY?
Okay.
you should add these,
They're both the same. So basically, what you do is you use the mid,
80.04.
like you multiply like the centers, like their x. I don't know how to describe it, but their coordinates of like their center of mass, you multiply them times each other.
add these together for I and Z.
So like the x coordinate of point A, and like the the y coordinate of A, and multiply it times each other. They multiply it times its mass.
IXX and IYY are different.
Really? That's crazy. So
Yeah,
something-
our IXX and IYY are different, but our ICZ stayed the same because it added up to the same value. I don't know how that happened, but okay. IX.
The calculation goes down one more time maybe.
Nine-
Next steps.
9.0507.
Let's not do the whole thing.
Are we sure that IXY is correct?
89.09. Okay.
Yeah.
M times distance.
Yeah, that we should make sure that's
Yeah.
right. Let's redo that one first.
So it's solid M x y. So what x is
Negative xy times dm. Well, the integral of the negative integral of xy dm.
x distance is 0.5. The y distance is 2.6. Okay. 2.8 times the x distance is 1.4. The y distance is 5. Can you add these into the negative? I don't know what it is.
25 and 2.6. 5.2 and negative 1. Then 1.4 times 0.5 times 2.8. Take the these, add them together.
That's what you did it right.
Okay, negative, and is the other one also, yeah, that would be the same? So put negative 11.32, put negative 11.32, put zeros, okay, calculate.
Man.
Oh, 7.29.
7.29.
Yes. What is, yeah, that's the most thing.
Okay, what was the xx and yy value?
XX is 80.04
Let's go.
and YY is 9.05.
Yeah.
You said 9.05.
No, I didn't say 9 because I never calculated y.
Then what did you tell me?
I said XX is 80.44.
But that's not x.
No, it is. It is.
No, it's y1. Oh. I said it's y1.
Oh, wait, it's
Why
YY.
is it
No, YY is 80. We switched it and that changed it. What? YY. Wait, YY is 80.
No, this is correct.
Was your
No,
matrix
bro.
like that, by the way?
No,
80.04?
No.
No, it was.
the center. It's y1.
80.04 was the center. Wait. So that means 80.04 is YY, not XX. We just completely switched those two terms. Wait, why is that? Because
No, we never had it right in the first place.
yeah, we didn't have
So
matrix.
A6 is integral y squared dA, and you take the other one is the other way around, right? So
Oh.
probably got it.
We probably just interchanged them in the beginning, and that's why. Yeah. Okay. But anyways, we got the right answer.
80.04, 905.
What? I had to do my
Like,
job.
that's my fault. It's not so-
Should we do it and then use one after?
I mean,
If it's, is it the long
we've
one
already
as well?
solved that
So,
one.
Is it the long one as well? So
mine is short, and it's solved already. So I can.
Mine is interesting.
Oh, okay. Here, you want to do it after lunch?
let's finish now.
Let's do it now. No, we can do it now.
Let's finish it. Let's finish it.
We got it. Let's do
We
it.
got it. We got it. Let's speed run it.
Let's finish.
Three questions. Three questions.
Okay, so I think we all
Let's do
have
some.
Is it three?
My last question, I didn't know, I didn't figure that out either. So
So what's the plan? You want to finish it now, right?
I also have an exam at 1:30.
Oh.
Yeah.
Ah.
I
Or how
thermal.
How about
You need to have lunch as well.
how about we try to figure out her question?
Afterwards.
Yeah. Yeah, we can do that. Sure. Yeah.
Figure out my question now or
Or how about we do our two questions,
Yeah.
eat lunch, and then we'll figure out the questions. We'll figure out your question after lunch, and then we're done.
Okay.
You want to do that?
Yeah.
Yeah. But we haven't seen it, so it'll just be our first time.
Yeah.
Hopefully it's not too bad. I think it's a spinning top, right? Okay.
Oh.
This is the last question. Yeah.
yeah.
Which one's yours?
It's
3.2. Yes.
I love oh. I love that the way we started. Our first homework is the way we're ending our last homework. We not finishing a problem.
All right.
No, that question is
This is personally my last problem. So I'm gonna try to do a good job.
Take off.
Yeah. Try to do my best in explaining this. So it's kind of a little bit further from what Minerva had, but you have this disc that's a little oddly oriented, rotating around a shaft. Before I do any of the math, I'm gonna conceptually show like the pathway that I'm gonna take. So from like a side view, this is kind of what we have. We have like two bearings supporting this spinning rod, and because of its orientation, it's generating a moment about its center mass, we call it MC. And we don't know what that moment is. It could be going like this, it could be going that way, it could be going this way. We don't know. So we have to figure that out, and based on that moment, these are supporting opposite and equal reactions. So if this is positive, for example, then these would have to be able to support a negative moment to counteract it, and some moments would be zero. So that's what's going on. So I'm gonna draw the initial reference frame. Alright, pretend it's center mass. Here we have the Z K hat direction. We have X I hat direction, and we have the Y here. Now, if we were to calculate our moments of inertia in this orientation, it would not be fun. Like you would get screwed over very quickly because
from our equation for angular momentum. If we tried to calculate these products of inertia on this orientation, it would all get very messy. And you could do it, but I'm not going to do it. So we can change the reference frame in order to make all the products of inertia go to 0, and then we'll just have a diagonal matrix. It's just a dot product with the angular velocity. So let's change the reference frame. Oh no. Forgot. That's tough. I'm not signing over.
You don't have to show each calculation. You can just.
So yeah, the new reference frame is going to look something like this. Z2. This was our Z1, or normal Z. It's rotated by an angle beta, which we're given. This was our X1. Also beta. This is now X2 in the I2 direction. And then the Y direction is equal to Y2, so J2 hat. And what this does is this ugly equation turns into, oh my god, IXX, 0, 0, 0, IYY, 0, 0, 0, IZZ, multiplied by the angular velocities. So rather than, like this has an angular velocity, 2 radians per second. In this format, it would be very easy to construct this matrix because it's just in the z direction. But this would be very complicated. When we change the reference frame, we make this a little bit more complex, the matrix of the angular velocity, but we simplify the actual inertia matrix a lot. So this is what we're going to be using. And I'm going to rewrite this in a easier to look at format. When you compute that matrix product, you get in reference frame B, the angular momentum is equal to, and then it's omega in the I2 direction, or whatever x component is, plus the J2 direction, plus ZZC times omega Z in the K2 direction. All right, so let's look at this term by term. We can do the inertia part really easy. So in reference frame B, the moment of inertia about the x-axis of the center of mass will be, just by definition, both the x and the y are 1/4 mr squared. If you imagine like rotating about y is the same as rotating about x because it's a uniform disk. So it's 1/4 mr squared, which also equals about the y. And then the z component is 1/2 mr squared. Okay, now for omega, because we made a transformation, this omega, we have to figure out what it is in our new coordinate system. So I'm just going to call it, that's omega. And whenever we do this transformation, it's going to be, there's some component. This is what the omega vector would be. It's something like this. So there's some component in the positive z direction and some component in the negative I2 direction. And that component is negative omega sine of beta. There's none in the y direction because that's like what it's rotating about. So omega y is 0. And then omega z is cosine of beta by trigonometry. All right. Whenever you do this, or like you plug in ixx, omega x, iyy, this actually goes to 0 because omega y is 0, and then you have the z component. This comes out to negative omega sine of beta over 4 in the I2 direction, plus omega cosine of beta over 2 in the, oh, sorry, these have MR squareds. And then this is the K2 direction. All right, so that's the first part. And now we want to figure out the moment. The moment is this, the cross product of the angular momentum with the angular velocity. So I'm gonna write this here. Equals omega cross the angular momentum. And actually this formula has another term, which is h dot, but we're told that the angular acceleration is 0. So obviously the rate of change of the angular momentum will be 0. So we don't care about that. So recall that the angular velocity vector will just be negative omega sine of beta I2 plus omega cosine of beta K2. So you would do this crossed with this, and this is I2, K2. This is also I2 and K2, so your cross product would be in just the J direction, which is, if you do that cross product, it is omega squared cosine of beta sine of beta mr squared all over 4. And this is in the J2 direction or the J direction, they're the same thing. And then you plug in all the values that we have everything, and this comes out to 0.608 newtons